Hello everyone, welcome to this new real analysis video. Today we are going to deal with order properties of real numbers. Last class we already studied algebraic properties. Today order properties along with some theorems. These theorems are taken from this reference book, and once we are done with this order properties of R, we can go and solve those theorems. Now let's revisit how we have approached algebraic properties of real numbers. For the purpose of studying algebraic properties of real numbers, we had to begin with 9 fundamental properties, say axioms. First four were related to addition, next four were related to multiplication, last one was distributive property, and we used these fundamental algebraic properties at a later stage to prove other algebraic properties. For example, suppose you are in a situation with two real numbers, you are adding those two real numbers and you are getting the second real number. It means that first real number is equal to 0, right? This algebraic property we ourselves proved in last class, but we had to come back to these fundamental properties. We had to use one or two or some of these fundamental algebraic properties to prove that algebraic property. I'll give another example. Suppose you are in a situation with two real numbers, a and b. Okay, and you are finding the product of these two real numbers, and the result you are getting as 0. It means that either a is equal to 0 or b is equal to 0. This is also a algebraic property which we ourselves discussed in last class, but by using one or two or some of these fundamental algebraic properties. It is the same approach we are going to use for the purpose of studying order properties of real numbers. This approach is comparable with what we have done in our high school with Euclidean geometry. For the purpose of proving Euclidean geometry theorems, we always had to go back to this set of axioms, 5 axioms. Now, coming back to our topic, order properties. What is meant by order properties of real numbers? If you are asking me the same question, I'll say order properties of real numbers refer to the notions of positivity or notions of inequality between real numbers. But unless you understand what is meant by notions of positivity or notions of inequality, there is no point of studying this definition. So, what is meant by notions of positivity? Suppose you are given with a real number, you can either say it is a positive real number, it is greater than 0. If it is greater than 0, you can say it is positive real number, or it can even be equal to 0, or it can be a negative number as well. Negative of that negative real number will be a positive real number. So, kind of these ideas altogether can be regarded as notions of positivity. Now, coming to notions of inequality. Suppose you have uh, two real numbers a and b. You want to say which one is greater than which one, or you want to say whether a less than b, or you want to say a is equal to b, or even a greater than or equal to b, a less than or equal to b. All these ideas altogether can be regarded as notions of inequality between real numbers. Now I hope that you understood the definition of order properties. Now what is the significance of order properties? Why we are studying order properties? Why? Because order properties helps us to understand how numbers are arranged, how real numbers are arranged, and how real numbers behave in a structured way. See, we have number line and all, right. In number line, we have in the left side negative real numbers, center 0, right side positive real numbers. There's a structure, and even we can derive rules of inequalities. We can do a lot of inequality manipulations. For example, uh, suppose you have three real numbers A, B, C. A is greater than B. B is greater than C. This will give the result that A is greater than C. This is a manipulation of inequality. So these kind of inequality manipulations can be done only by using order properties. And we can explain limits, convergence, continuity, differentiability only if we have a clear-cut idea about order properties. Why? Because these topics like limits, convergence, continuity, differentiability, they include the idea of neighborhoods, idea of left-hand limit, right-hand limit, and defining intervals. All of these, we need order properties. Now let's start studying order properties. In perspective of notions of positivity, we have three properties. First one, if A, B belongs to set of positive real numbers, this P indicates set of positive real numbers, then sum of A and B belongs to the same set. Second property, if AB belongs to set of positive real number, then its product belongs to set of positive real numbers. Third one is more important. Um, it has got a name trichotomy property because this property divides set of real numbers into three distinct types of elements. It goes like this. If A belongs to R, then exactly one of the following holds. A belongs to P, A is equal to 0, minus A belongs to P. This is true. You can test it by taking one or two examples. Suppose you are given with minus 2, then minus of minus 2 belongs to set of positive real numbers. Or it can be 0, or the given number can be a positive number as well. If you want to get the essence of this trichotomy property, just read this. It indirectly tells that this set of negative real numbers has no elements in common with set of positive real numbers. Moreover, set R is the union of three disjoint sets. Which are those three disjoint sets? First one is set of positive real numbers, then singleton set 0, then lastly set of negative real numbers. Union of these three disjoint sets will give set of real numbers. Now, in perspective of notions of inequality, let's see some properties, but you should have some basic knowledge about the usage of this symbol. If A belongs to P, we say A greater than 0. If A belongs to P union singleton set U is 0, then A greater than or equal to 0. We say A is non-negative real number. If minus A belongs to P union 0, we can write A less than or equal to 0. We say A is a non-positive real number. In similar way here, positive real number is that if you want to say negative, if you want to represent negative real number, just write A less than 0. Then minus A belongs to set P. And just eliminate this singleton set 0 here and eliminate this equal to sign here. Minus A belongs to P implies A less than 0. We can say in that case A is a negative real number. Now coming to our main topic. We have two properties here. First one, A minus B belongs to P. We can write A greater than B or in inverted form as well, B less than A also. These both are equivalent. If A minus B belongs to P union singleton set 0, then A greater than or equal to B or inverted form B less than or equal to A. These all are very basic. Now try to link trichotomy property which comes under notions of positivity with the property of related to notions of inequality. See, trichotomy property implies that for AB belongs to R, exactly one of the following will hold. We are trying to apply trichotomy property into the case which contains two real numbers. See, A minus B belongs to P means what? A minus B greater than 0. If we are simplifying it, we can write A greater than B. If A minus B is equal to 0, that's also one case in trichotomy property, right? Then A is equal to B. If A minus B is less than 0 or B minus A belongs to P, then we can write B is greater than A or A less than B. If we are simplifying that notion of inequality, we will get this inequality A less than B. Now, if both A less than or equal to B and B less than or equal to A hold, then A is equal to B. Why? Because here you can um, you can explain this in the form A minus B less than or equal to 0. Here B minus A less than or equal to 0. So basically it's like A minus B less than or equal to 0, A minus B greater than or equal to 0. Two numbers which can be greater than or equal to 0, which can be less than or equal to 0. then obviously it should be equal to 0. So using trichotomy property, if these two holds, then A is equal to B. Now let's prove each theorem one by one. First theorem, it has got three parts. Before going on proving theorems, I would like to say all of these theorems are order properties itself, some extensions of order properties. So focus on how it is getting proved. It will help you to understand the significance of order properties. Don't focus on this statement part, focus on the proof. Coming back to the theorem. First part, A greater than B, B greater than C implies A greater than C. A greater than B implies A plus C greater than B plus C. C can be 0 or positive real number or even negative real number. It doesn't matter, but A plus C greater than B plus C. Third one also just read it, A greater than B. If C greater than 0, CA greater than CB. If C less than 0, CA less than CB. Let's see how it is getting proved. First part, A greater than B means A minus B belongs to P. B greater than C means B minus C belongs to P. See, we have two positive real numbers. Addition of two positive real numbers will give another positive real number. So A minus B plus B minus C is a positive real number. Solving it, A minus C belongs to P. We will get like this. Hence, A greater than C. A minus C belongs to P means A greater than C. We already seen that kind of operation in last slide. Coming to second part, A minus B belongs to P. In order to reduce this inequality, add C and subtract C on the same part. A minus B, add C and subtract C. You will get something like this, which is nothing but A minus B. We already know A minus B is in P. This implies A plus C minus B plus C is in P. Finally, we can write A plus C greater than B plus C by using inequality symbol. Coming to third one. See, this is compared to first and second part, third part is a little complex. A minus B belongs to P, C belongs to P. Then multiplication will be a positive real number. That's okay. C of C into A minus B is in P. Opening, yeah, CA minus CB is in P. CA greater than CB. This is the case when C greater than 0. Now coming to C less than 0, you have to do an extra step. C less than 0 means C is not a positive real number. But according to trichotomy property, minus C belongs to P. So if we are multiplying A minus B with minus C, we will get a positive real number. So we can write CB minus CA belongs to set B. CB is greater than CA. This is the case for C less than 0. Let's move to next theorem. This theorem states that if A belongs to R such that A is not equal to 0, then A square should be greater than 0. Next is 1 greater than 0. Next is if n belongs to set of natural numbers, then n greater than 0. How we are going to prove this? Let's see. By trichotomy property, A not equal to 0 means either A belongs to P or minus A belongs to P. Now, A belongs to P, A square is equal to A dot A. A product of two positive real numbers give positive real number. Now, minus A belongs to P means A square is equal to minus A into minus A. Since these two are positive real numbers, its product will also give positive real number. A square is a positive real number. So whenever A is not equal to 0, we can conclude that A square is greater than 0. Now, second one, 1 greater than 0. How to prove this? We know that 1 can be expressed as 1 square. So in place of A, just substitute 1 to get a 1 greater than 0. Moving to the third part of this theorem, if n belongs to set of natural numbers, then n greater than 0. For the purpose of proving, we have to use mathematical induction. For n is equal to 1, the assertion is true. 1 greater than 0. It is also already proved in the second part. Suppose for an arbitrary natural number, this assertion hold. Then we have to show that k plus 1 greater than 0. This is our task. We know k belongs to p, that's our assumption. We know 1 belongs to p. If there are two real numbers which are positive real numbers, then its addition will give another positive real number. So k plus 1 also belongs to p. In terms of a symbol of inequality, we can express it as k plus 1 greater than 0. So using mathematical induction, we proved that if n belongs to n, n greater than 0. Before proceeding to next theorem, I would like to present a very useful fact that no smallest positive real number can exist. Whichever positive real number you take, you will get a lesser real number than that. That's the main essence behind this. How to prove? Suppose you are taking an arbitrary positive real number a greater than 0, then half a is also greater than 0, right? Because a is a positive real number, half is also a positive real number, product is also a positive real number. We have this inequality 0 greater than half a greater than a. Thus, if it is claimed that a is smallest positive real number, we can exhibit a smaller positive number half a than a. Instead of half, you can take 1 by 3, 1 by 4, whichever fraction you want, but it should be a proper fraction. This fact will help us to understand this theorem. Statement is, if A belongs to R is such that 0 less than or equal to A less than epsilon, or every epsilon greater than 0, then A is equal to 0. Here what they are telling. See, A is greater than or equal to 0. But at the same time, A is less than an arbitrary positive number. If this is the case, then A is equal to 0. To prove this, we use the method of contradiction. Suppose instead of 0, a greater than or equal to 0, just let it be a greater than 0. Okay, eliminate that equal to. Let it be a greater than 0. But if you are taking epsilon 0 is equal to half a, this is also a positive number, then we will be having this inequality. But it is against this statement. Let's see by reading this. It is false that a less than epsilon for every epsilon greater than 0. See, epsilon 0 is greater than 0. So we can't say for every epsilon greater than 0, a is less than epsilon. This inequality is violated if a greater than 0. So in order to hold this inequality, we should be having a is equal to 0. Hence, we conclude that a is equal to 0. Read it again, you will understand it's nothing but the method of contradiction. Now, you have a note. To show that a number a greater than or equal to 0 is actually equal to 0, we see that it suffices to tell that a is smaller than an arbitrary positive number. This is nothing but what is meant by this statement. Okay. Next theorem. This theorem states that product of two positive numbers is positive. But positivity of a product of two numbers does not imply that each factor is positive. It means that suppose you have two numbers and multiplying it, you are anyway getting positive product. But it doesn't ensure that each factor is positive. Mathematically, we can write like this: a b greater than 0, then either a greater than 0 and b greater than 0. This is not only the case can be like this as well: a less than 0 and b less than 0. So each factor can be both negative at same time. So this is the theorem. How to prove it? First, we note that a be greater than 0. This is already given. Then a is not equal to 0 and b is not equal to 0. You will be having a doubt how we got a not equal to 0 and b not equal to 0. For this, we have to go back to algebraic properties of real numbers. From the trichotomy property, either a greater than 0 or a less than 0. This is certain. A not equal to 0, then a should be either greater than 0 or a less than 0 based on trichotomy property. If a greater than 0, then 1 by a is greater than 0, right? If we have a positive real number, then its reciprocal should also be a positive real number. Therefore, b is equal to 1 by a into ab is greater than 0. ab is positive, 1 by a is also positive. And product of positive numbers will give positive real number, that is b. Similarly, if a less than 0, then 1 by a is less than 0. So 1 by a multiplied by ab. 1 by a is a positive number, negative number. ab is positive number. Multiplication of positive number by negative number will be giving negative number. So b is negative real number. In that way, we have proved this. This theorem is followed by a corollary. If a be less than 0, then either a less than 0 and b greater than 0, or a greater than 0 and b less than 0. As it is a corollary, it needs no additional proof. But if you are able to give an explanation, it will be good. So try to work on this and try to find a good explanation for this. Thank you for watching this video. In the coming classes, we will discuss further topics related to real analysis. Thank you once again.